Thanks, Jana. Can you guys hear me okay? Yeah, my name's Mary Ford, and I just want to give a really brief overview of Maracus, the Mid-Atlantic Regional Association Coastal Ocean Observing System. We are a nonprofit, and we're one of 11 regional associations that make up the U.S. Integrated Ocean Observing System. We're spread throughout the country on the coasts and in the Great Lakes. The regional associations are. Maracus actually covers from Cape Cod to Cape Hatteras. And we're comprised of 10 states, including and plus DC, and 5 estuaries, including Chesapeake Bay, over 78 million people, and the amount of data collected in this area is incredible. We as Maracus collect and serve our own near real-time observing data, but we also integrate a lot of state, local research and other types of data into our tools. And it's these local institutions and state and community partners that are really critical to what we do and delving into the real needs of the community. Our data are federally certified, which means that the data are as good as or better than data served on federal platforms. So it can be used in a lot of high-level decision making. And our tools are incredibly robust, but they're really easily customizable and usable, which Sherry will showcase later on in the agenda. Jana, you can move on to the next slide. What's different about us, other than some other research groups, is we're not a research group. We're very stakeholder driven. And we're really able to dig deep into the regional and local needs of the communities. We emphasize partnering with the local experts and the community leaders, and focus on amplifying efforts, not duplicating them. And this is all just to provide the best data possible for decision making. We do have 5 different theme areas, which are pretty all-encompassing for folks who live on the coast, which you can see them on the slides. Today, we're really going to specifically be talking about our enhanced water level observation and tools initiative and focusing on Virginia. Maracus data support so many different types of observations, models, tools, including the CBEFS model run out of VIMS. And we are going to delve into that model and some other Virginia tools later on in future webinars. But today we're going to be focusing on the water level stuff. So we don't ever hesitate to reach out if you have data to share or thoughts about things. But with that, we'll go ahead and get on to the fun stuff.
All right, everyone. Well, next we're going to have Maracus's water level manager, Tina, give a brief overview of the WWW, so water level, wave, and webcam project. Go ahead, Tina, take it away.
Can everybody see my screen with the PowerPoint? Oh, awesome. Sweet. Oh, 1 second, my computer is a little slow today. Okay, cool. Awesome. So, hey everyone, my name is Tina Sepulpour. I am the water level project manager here at Maracus. I appreciate you guys being here today. So before we dive into the Virginia specific work, I want to give you a quick overview of the broader regional efforts that's going on in the Mid-Atlantic. So to start off, coastal communities in the Mid-Atlantic are facing more frequent and severe flooding. This can be anything from sunny day tidal flooding to storm surge and compound events, which is getting harder for local officials and planners to respond effectively. One of the things we hear over and over again is that we need better data in real time and more collaboration across states. And with this project, it's helping making that happen through sensor deployments and hydrodynamic modeling. We call this the Wave, Water Level, and Webcam Project, or 3Ws project for short. While this is part of a broader national effort led by IUs, today we're highlighting the work that's happening here in the Mid-Atlantic. So this project is a collaborative effort across 5 states supported by the Inflation Reduction Act that's helping coastal communities access the data they need to better prepare for flooding and building long-term readiness. So this effort includes deploying low-cost sensors, water buoys, wave buoys, ADCPs, webcams, and building hydrodynamic models to better track and forecast coastal flooding. The data we collect feeds directly into tools used by emergency managers and planners, helping communities better prepare for things like storm surge, nuisance flooding, and wave impacts. And one of our big goals is not to just make this data stay local, but we're working to align it with national standards so it can be used in federal platforms like co-ops and eventually feed into NOAA and National Weather Service tools. Ultimately, these efforts improve real-time awareness and support the long-term resilience planning across the region. So we've been collaborating closely with the weather forecast offices to improve local modeling and forecasts by sharing the data we're collecting through this network. But this isn't just about pushing out data. A big part of this is really building that two-way conversation with communities. So we want to hear from you and know what kind of data would be most useful in your day-to-day work or planning. So this first year is really about listening and learning. Where are the gaps? What's missing that would help you plan or respond to flooding better? We're also making sure that we include a wide range of voices, such as tribal, local, and regional partners, because each community has different needs and priorities. You'll hear more about this shortly from Sherry, but OceanMap is one of our customizable data platforms that we use. And we would really like to know, what would you want to see from it? What would make it more useful for your team? In the end, this is a collaborative project, and the input we get from you directly shapes the tools that we're building. So we are working with and partnering with University of Delaware, University of Maryland, Stephen Institute of Technology, Monmouth University, and Virginia Institute of Marine Science to enhance this monitoring across the Mid-Atlantic. And although each state is tailoring their approach to meet local needs, in the end, we are all sharing common goals, such as improving flood forecasting and early warning, supporting community readiness and adaptation, and integrating this data into national and regional tools such as OceanMap. So now that I've kind of given you an overview of the 3 Ws as a whole, I'm going to briefly talk about what our other partners are doing in other states. So the first one is University of Delaware. This project is ran by Dr. Jack Palayo and Dr. Alexandra Schuler. So their 2 main goals with this project is to assess local communities with coastal process understanding and provide real-time knowledge for data dashboard use, and install a wave buoy network for offshore modeling and forecasts. On my slide to the left, there is a map with red pins on there. Those are the proposed buoy locations where we're planning on setting out SOFAR buoys that will be giving us hourly updates. There is ongoing engagement right now to figure out where we want to put those water level sensors. So after that is University of Maryland, which is run by Dr. Tim Canty. So this project is part of the university's HydroNet and Climate Resilience Network that builds on University of Maryland's Grand Challenges work that started as a pilot program testing sensors in Annapolis and talking to local partners around Maryland. So the goal with this is to expand the low-cost water level sensor network in Maryland and around the Chesapeake Bay. They're focused on data deserts, which are areas along the Chesapeake Bay that don't really have real-time sensors of any kind, better yet, water level sensors. So right now they have currently deployed 10 Hohonu sensors on the eastern shore, and are currently looking to deploy other sensors throughout other parts of Maryland. So there is ongoing engagement to determine these locations with the highest needs for these sensors. And last but not least, so this is kind of a bit of a partnership between Stevens Institute of Technology and Monmouth University, which is run by Dr. Philip Orton, Dr. Laura Kerr, and Dr. Tom Harrington. So the goal of this project is to create a higher resolution, shallow water barrier estuary model to improve water level predictions. So there has been regional planning in the state, but there's still a lot of flooding problems that they're dealing with, such as nuisance flooding and sunny day high tide flooding, especially in low-lying areas in the barrier island. So what they're going to do is focus on data collection both over land and in water using a SOFAR buoy, ADCP, and water level sensors. So using the SOFAR buoy, they want to see if it'll work well in the back bay areas that have shorter periods and smaller waves. They are currently working with communities to identify which areas are best suited for these water level sensors. And along with this, they're utilizing data collection apps like MyCoast to collect photos with time and location stamps to see where flooding is happening. This will help verify flooding close to tide gauges or even in areas where there isn't a tide gauge nearby. This also will help verify their flood model that they're building, which they hope will help create accurate forecasts using the Stevens Flood Advisory System. So that's kind of overall what the 3Ws are. This to kind of wrap it up, the region's network of sensors combined with OceansMap is giving communities the tools they need to understand and respond to these coastal changes. We're really proud to support this work across the Mid-Atlantic, and we're excited to see what happens in the next 5 years with these projects. I have my email address on there. If you guys want to reach out or have any questions, feel free to do that. And with that, I'll pass things over to Dr. Derek Loftis. He is an assistant professor at the Virginia Institute of Marine Science and leads our water level work here in Virginia. He's been doing a lot of great work here and around the area, so I'll let him take it from here and share more about what's happening with his work in Virginia.
Great. Thank you very much for that introduction. I really appreciate it, Tina. So I've had the privilege of working on this project that's really focusing on flood monitoring and flood model validation using next generation water level sensors and community science data. Now these are essentially just some of the tools in the arsenal of a person that handles flood prediction. And so, of course, the goal with this is to improve the forecasts that are being provided for inundation prediction systems. In this case, most of the models we'll be talking about today are storm tide models capable of predicting storm surge and tidal flooding and a combination of both. But the ultimate goal is to fully incorporate rainfall-induced inundation as well through compound flooding when it pairs up with storm tide. So these types of things are really at the precipice of the modern research approach that we're looking at and working to embody in this endeavor. So the overview of my talk is going to first kind of introduce sensors and a platform of water level sensors in the Tidewater region of Virginia called StormSense. Next, I'll be talking about some next generation water observing technologies, leveraging machine learning and artificial intelligence through live webcam sensors as a new type of passive remote sensing technology we've been working to develop in collaboration with the U.S. Geological Survey. And then the third step for this is going to be introducing how we actually do storm tide forecasting and specifically also how we handle tidal forecasting. Then we'll delve into automated alerts connected to these water level sensors as one of the key resources that a lot of communities that are partnering with the whole instrumentation proliferation approach that's used with the StormSense project and others. Our goal is to provide some automated flood alerts that provide some credits to the individual communities that are attempting to be more resilient in these efforts. That provides some kickbacks to them through the community rating system through the National Flood Insurance Program. So automated alerts are important. And then, but also what types of filtering are involved so that you don't send erroneous flood alerts because that ultimately provides less intrinsic connection to the system for individuals that are involved because they're less willing to trust future flood alerts. And so our goal is to kind of make sure that we are streamlining the data that are available through application programming interfaces, and then featuring flood validation of models that are driven by these sensor data. A lot of the work that we published previously has been available in the Marine Technology Society Journal, that's been looking at the intergovernmental blueprint for community resiliency. And so, just kind of as a pictorial outline of what I'll be covering today, I'm the lead for the StormSense project. It's won several awards related to flood prediction driven by sensors. And so real-time observation data provide us additional context to what's happening. We've got over 65 water level sensor locations at this point, and we are incorporating data from NOAA and the U.S. Geological Survey on the federal level, along with state data from the Department of Emergency Management in Virginia. We try to transparently share these data. They're geocoded using geographic information systems. The open API links or application programming interfaces mean people can ingest these data into their systems for actionable emergency management decision making, but also for community planning purposes in the context of sea level rise. They're also able to look at the data from past events and incorporate that into future community planning. And so the reason why this is important is mostly because if you look at the highest astronomical tides of today, that can kind of give you a very brief glimpse into what you would expect to be the mean tide level 20 to 50 years from now, depending on which projections you're looking at for actionable decision making. And so with that, we have 65 water level sensors that are tide gauges within the tidal region of Virginia. There are even more water level sensors in the riverine environments beyond the fall lines of the James River, the York River, the Rappahannock, and Potomac rivers as the major tributaries of Virginia. You can interactively access these data at the web link below. The collaborators of the StormSense project in the city of Virginia Beach at vbsensors.bvgov.com. You can access these data directly and see they're highlighted based on when any moderate to minor flood conditions exist in those areas. And so this network exists of data that are incorporated from NOAA's water level sensors. There are 7 of them in Virginia. Additionally, this sensor network also incorporates the Washington, D.C. sensor, technically outside of Virginia, and also Bishop's Head as another NOAA co-ops station that's incorporated within this network of sensors. But strictly speaking, there are 65 within the bounds of Virginia currently, and our goal is that we're currently working to deploy 4 more new water level sensors in 2025 through funding provided by Maricus. Now, within these individual organizations, we all, interestingly enough, have different directives in terms of what our goals are, but ultimately, all these individual organizations have focuses on observations for different reasons. And so as a result, the data that we're collecting are being aggregated so that you don't have to go to lots of different websites in order to access this information. The communities that we're working with and partnering with for these efforts do not typically have large offices of people with GIS departments for handling geospatial flooding, or other groups that are specifically focused on emergency management when there's a major flood event that's coming. And so our goal is to aggregate the data quickly where they can find it in one place, but also still access through the links the original data sources for their own analysis. Now, within the StormSense program, as I mentioned earlier, we're ingesting data from a variety of different sensors, and that means the hardware and ultimately the purposes of why those sensors were deployed are inherently different. And so it's important to kind of acknowledge what those differences are. Ultimately, the premier example of monitoring through the National Oceanic and Atmospheric Administration is they're collecting lots of data through full weather stations. At a lot of their locations, they're collecting wind speed, air pressure, all of those things are incorporated into our storm tide predictions because storm surge is driven by winds and atmospheric pressure. On top of that, we're also using the water level data from these sites to help us inform our model's accuracy. And those sensors are using high-resolution Ka-band radar, so it's a non-contact water level sensing technology, kind of a near-field remote sensing approach. Most of these radars are within 50 feet of the water surface, and they simply emit pulses of microwave radiation at the water surface, and they can measure this up to 1 millimeter accuracy. Now, the cost for these water level sensors are usually between $35,000 to $50,000, but they get extremely accurate results as they are calibrated in laboratory settings and then tested again in the field. Next is the U.S. Geological Survey. They, of course, also have an observation-based focus as their programmatic directive as a federal agency. And a lot of their work also provides not just boundary conditions from our hydrodynamic models in the context of flux boundaries at the fall lines of the major estuaries of Virginia, but we also use the data from their Ka band radar sensors, and those are typically accurate to 3 millimeters of accuracy or less. And so they're very high resolution as well. And their sensors cost slightly less at about $26,000 to $30,000. And these are based on last year's US dollars in 2024. So in the context of inflation, they're slightly higher than that now, but they do an excellent job of monitoring those things. And so ingested into StormSense now, of course, we have two different types of sensors that we are using within our communities. There are a couple of different vendors that handle this as well. And so we have been using some ultrasonic sonar and Ka band radar sensors. The sonar sensors are accurate typically within about 2 to 3 centimeters, depending on whether or not you have a storm surge event taking place or if it's just typical tidal conditions. The radar sensors are, as we field tested them, accurate to about 2 millimeters in accuracy relative to the root mean squared error method of measurement. We've tested this by co-locating sensors next to NOAA and USGS sensors in the past in these communities to ensure that the relatively lower cost of these sensors is low cost, low energy water level sensors are not acting at the detriment of accuracy from a scientific perspective. On the other side of things, we also have some rapid deployment gauges, as we kind of call them. Basically, we temporarily will deploy these during major storm events, and they can be bracketed to light posts or other places that are believed to be in the path of inundation. They help us enhance the prediction of our models by temporarily deploying water level sensors. And then finally, our newest generation of sensors, we're calling this the hardware, the StormSense VIMS, or so named for the Virginia Institute of Marine Science where I work, but it's a video inundation monitoring system, and it has an algorithm on board called Flood Vision AI that essentially is allowing us to incorporate in real time water level imagery that's coming in from oblique pictometry collected by these web cameras, and it's translated into water levels using 4K resolution infrared camera that's on board, and then taking that information and translating it into water levels using edge detection and machine learning. So if you're not familiar with how these different types of near field active remote sensors work, we focused on these primarily because they don't require very much maintenance relative to in situ pressure transducers where biofouling is a problem. In this case, usually algal matter will kind of collect around pressure transducers, and that translates to additional maintenance, but also lack of accuracy in terms of water level prediction, since the pressure around those types of transducers is kind of fogged by increasing layers of algal growth on them over time. And so because of that, all the water level sensors in StormSense are active remote sensing technologies that are leveraging the benefit of not being in the water, but being able to measure the water elevation by non-contact methods. Typically, these sensors, we apply for grants to help defray the sensor costs, then order the sensors and assemble them. Depending on the context, we'll use radar or ultrasonic sonar. The reasons why they're different is because Hampton Roads in Virginia, where we deploy most of these sensors, has a lot of military bases. And there's a lot of interference on each of those different spectra for different reasons when military training or operations are taking place. Next, we then take the water level sensing data and conduct a tide watch over 12 hours to kind of give us the highs and lows of the current tidal fluctuations, then revisit that at 1 month and then every 3 months after that to ensure that the seasonal values are appropriate. Then we translate the data from 4 to 20 milliamp measurements of distances to the water to relative datums to make sure that those data are important and relevant to the individual locations they're being collected. That we then incorporate a spike filter for automatic alerting. This ensures that if some random piece of debris or object below the surface is there, that it's not artificially sending out alerts saying, hey, it's flooding at the sensor, when really there's maybe someone fishing from a boat underneath a bridge that happens to be under the sensor at the time. It doesn't register that 2 to 3 foot increase by hitting the boat deck instead of the free surface of the water as flooding, because then that causes people to not believe that the flood alerts are relevant in the future. We also use high frequency waveform smoothing because sometimes there's instantaneous waves underneath those water level sensors, and we want to be measuring the mean values, so they're also energy conservative. These water level sensors are collecting data every 6 minutes, and they go to sleep for 5 of those 6 minutes, then wake up, collect data over a 60-second period of time, and average those values into a single instantaneous value that's recorded in the cloud before it goes back to sleep for the next 5 minutes until the next 6-minute measurement is recorded. Now, in terms of StormSense's sensor accuracy, when we first started deploying these in 2018 to 2020, there was this initial question of whether or not the relatively cheaper hardware that we were using were at least relatively as accurate as the federal sensors. And because the goals of a lot of these communities are trying to determine whether or not individual sites are in the floodplain and whether they should obtain optional risk insurance, we conducted a study to compare the differences by mounting some of our sensors to the same sensors as the U.S. Geological Survey's sensors in the city of Virginia Beach. Since they had multiple USGS sensors there, we deployed them at 4 different locations on the same bridges, but a good distance apart, just to ensure that there's no interference. In most of these cases, we're using ultrasonic sonar sensors instead of the Ka-band radar, so obviously already they're not in the same frequencies to begin with, so they shouldn't be interfering with each other, but just for the purposes of comparison, we were using some ultrasonic sonar sensors, and the hardware for those sensors were roughly $3,000 at the time we conducted the study in 2018 to 2020. And then we compared the data over a 4-month period of time, comparing them relative to the infrastructure used by the U.S. Geological Survey's sensors. And while our sensors were not as accurate as the ones deployed by the U.S. Geological Survey, we did find that the aggregate root mean squared error among these 4 sensors from November 2020 to March 2021 was accurate to within plus or minus 1.18 centimeters. And during this period of time, there was a king tide in November and 4 minor nor'easters in January and February that took place. So we had some pretty significant amplitude minor inundation events that took place that allowed us to compare pretty reasonably a mix of regular tidal conditions with extra tidal conditions. Now, next, as I mentioned, we've been deploying new water level sensors, and so it's often interesting for folks to see some of the challenges that we encounter with this, but also the benefits of partnership. In this instance, last year in spring of 2024, in partnership with the Chickahominy tribe, we deployed a new water level sensor on a dock along the Chickahominy River that feeds out to the James River in South Chesapeake Bay. And this water level sensor is maintained by one of our vendors, Greenstream. It was integrated into the StormSense platform in June 2024. Now, typically the next step with this is that we like to take the water level sensing data that we have and provide 36-hour tidal forecasts in those locations. Through harmonic decomposition of the influence of the sun and moon in these tidal areas, we can provide forecasts up to 36 hours in advance as a kind of rolling window moving forward. So as we were working to integrate these data into the VIMS Tide Watch charts to provide these forecasts relative to the North American vertical datum, for it's the geodetic datum that's used for providing land survey information, and for people trying to obtain flood insurance, that gives you your freeboard standards as well. But we also relatively convert these to tidal datums. So if water is your basis, then the mean lower low water datum as well is provided. Now, as we started going through this process, a significant portion of our effort involves survey benchmarking and translating those data to the appropriate vertical datums that we need to use for actionable decision making. So as we deploy the water level sensor, you'll see that basically the sensor box along with the sensor itself kind of consists of the solar panel along with the water level sensor, the battery inside that's recharged by the solar panel, and then of course finally the data logger and the antenna that transmit this information first to the cloud using cellular broadband data or satellite, depending on how remote these locations are. And then, of course, as a lot of planning goes into deploying these individual sensors and coordination with community partners that help make this information available. One of the weird anomalies we encountered in 2024 was the convergence of these different cicada swarms that were taking place. And so as we were preparing for hurricane season to start in June of 2024, we had a lot of weird anomalies under our sensors in a couple of the new locations that we were deploying. And one of the worst spots that we saw this was in the Williamsburg area at the site where we deployed a new water level sensor last year, the Chickahominy tribe. And this was simply a convergence of the two major cicada swarms that were taking place at the time. They were large enough insects that were swarming underneath our water level sensor. We had a lot of strange data spikes that were occurring at this location. It was very hard to calibrate the sensor for about 2 months of time at this location. And so thankfully we haven't had that as an issue this year, but it is one of those interesting environmental idiosyncrasies that you run into of one site that may not be so bad at other locations. But anyone who lives in South Chesapeake Bay near the water, a lot of the sound of the droning of the cicadas carries over the water very well. And so our ultrasonic sensor struggled a bit with just the size of the individual insects flying underneath the path of the ultrasonic sensor between it and the water at the dock at this location. But thankfully, it was not an issue with our newest water level sensor at StormSense. We deployed this in June of 2025 along the Pamunkey River in partnership with the Pamunkey tribe on their reservation there in King William County. We're currently working on integrating tidal forecasting in this newest site that was just deployed last month. Now, typically we want at least 30 days of water level sensor data just to provide us at least a mean value that we can incorporate into the model for tidal decomposition. And at that point, then we can start to provide amplitude, phase, and frequency forecasts for this location looking forward. And so that should come online in the next few weeks for this particular location. 3 more water level sensors are planned to be deployed in Virginia's Middle Peninsula region. Or kind of finalizing the site surveys to make those deployments happen, ideally before the fall tidal flooding season. And finally, 6 new water level sensors are planned for deployment next year in Hampton Roads in 2026, and 3 of those sensors are based on some new next generation water observing technologies leveraging AI to make their deterministic identifications of water level. So here's an example of what this looks like. This is a prototype for what ultimately became the video inundation monitoring system. It uses a web camera using 4K resolution night vision and edge detection, as you can see kind of highlighted there with green lines here. This is an example of Hurricane Florence in 2018 when we first started testing this technology with an Amazon Web Services Deep Lens camera that we had won as part of an award that we had received for StormSense based on our initial efforts in proliferating water level sensors in urban and rural communities in Virginia. It essentially translates those pixels to depths for flood monitoring. And so while we started deploying some of these water level monitoring technologies ourselves, one of the things that we started doing immediately as one of the weak points that we first found when using this technology is that the deep lens camera couldn't see at night. And so we started using water level sensors that were capable of seeing things at night. And in partnership with the U.S. Geological Survey, they have lots of web cameras throughout the continental United States in their platform called HiViz. And so this particular platform has lots of reservoir cameras and stream flow cameras that give us a very quick description of what's happening in those locations, and they're extremely high resolution. They have 4K resolution, but they also, most importantly, have infrared night vision, so you can see water levels 24 hours a day. And so we've been training a machine learning model along with an edge detection model to help us identify pixel values to extract free surface elevations of the water for stage determination. And of course, the natural strengths of these types of models is that you can see what's happening in the field of view of these cameras. And emergency managers love this because they can very quickly see that indeed there's flooding that's happening when they see critical thresholds being reached by these types of cameras. It will draw their attention to them, and they'll be able to view and see whether or not indeed flooding is happening within the field of view of the camera, or if it's some random obstruction that's in the way of the camera. So as I mentioned, some of the weaknesses that are involved with this is, of course, you've got to be able to see. So fog and heavy rain can be problematic for these types of sensors, which are not weaknesses of radar sensors. And so kind of a mix of the different technologies really help us get a very good idea of what's happening on the ground at locations that are subject to inundation. Also, of course, because it's a camera, it's more energy efficient because it's not emitting pulses of radar or ultrasonic sonar, so it doesn't require as much energy to operate. But on the negative side of things, it is a little bit more difficult to determine things that are happening due to light attenuation from dawn and dusk, when the sun or moon might be in view of the camera directly within its field of view, or the reflection of the sun and moon are visible on the surface of the water if it's very still. This also can be problematic as the natural balancing and focus of the camera are a little bit more challenging when there are extremely bright objects in view. And so, as you might would imagine, we've been translating these free surface water elevations predicted by a machine learning model in collaboration with this new research that we've been conducting with the U.S. Geological Survey for the last couple of years. And so we have a machine learning modeled water elevation in blue. And so in some instances, you can see the model struggles to figure out whether or not the reflection of the water is the free surface elevation, or if it's something else, if the water is extremely still. And so relatively to mild turbulent waters do a pretty good job of predicting typical tides, but also if there's a lot of fog in view of the camera. That's another thing the sensor struggles with. If it can't see its target field of view, that's also challenging because it now can't see where the water is to determine whether or not the elevation is at a particular spot or not within its frame of reference. Now, overall, our root mean squared error with this type of model, just showing an example of some of the data we recently published in the Journal of Applied Ocean Research last month. The root mean squared error for some of our initial tests with this in January of 2022 was plus or minus about 3¼ centimeters, which we were pretty excited with for a camera that's within about 50 feet of view. In this instance, we've got a web camera about 20 feet from the target area, but of course this is proportional to distance, as a camera's pixel size and density differs depending on how close it is to the object of interest within its field of view. And so, getting into the science a little bit, our final machine learning model that we validated in January of 2022, basically it's collecting images every 6 minutes. This translates to almost 7,200 images collected over the month of January. And for that 720-hour period of time, the mean absolute error was plus or minus about 0.71 inches. And that was pretty exciting for us because about 80% of those predictions were accurate to within 0.05 feet or within roughly 0.6 inches. Whereas another 17% of them that were slightly less accurate were accurate still within about 3.6 inches, and only a few of them were wildly outside of the range we were hoping for and greater than 1 foot from the actual observed water level. And as I mentioned earlier, that was mostly atmospheric conditions that were not conducive for monitoring. So we've been working to incorporate flags associated with those particular machine learning outputs to indicate that the model's not very certain in these instances of what's happening. And now it's getting to the point through object recognition where it's starting to identify whether the conditions are fog or rainfall, and whether it's nighttime versus daytime fog, and those types of things that help us identify the specific conditions where the deviations were greater than 1 foot. And this is based on training data that were posted on ScienceBase from Paul Renaud and Keegan Johnson in 2024 from the U.S. Geological Survey. And we were able to recently publish these results in an article in Applied Ocean Research in June of 2025. Now that we've got water observing data from a variety of different types of sensors, we have automated alerts connected to many of these types of water level sensors. We coordinate this effort with the National Weather Service, along with other local offices of emergency managers, just to ensure that we're not putting out differing information from what the advisement of those individual groups and organizations are. The city of Newport News specifically has taken data from their water level sensors. And in fact, they recently had all of their sensors updated by Greenstream in the last couple of months with the latest technology. And essentially, they established critical flood alerts at different locations. This is an example of a non-tidal water level sensor, but a large amount of rainfall that took place a couple of years ago in August. At the end of July, triggered this alert that eventually sent out information so the communities will use this information to help validate the conditions on the roadways and in different places where the transportation infrastructure or actual infrastructural assets are adversely affected by flood damage. And this information is also useful from the context of providing automated alerts. This is helpful mostly because it not just only provides additional credits through the National Flood Insurance Program's community rating system maintained by FEMA, but there's also the benefit of these water level sensors providing actionable information to people that are subscribed to these locations. And so this kind of provided some tangible cost savings for people in special flood hazard areas in these cities. But on top of that, the automated alerts help people decide which directions they might want to travel on their commute home from work if they're subscribed to these locations within Newport News. Now, of course, if you're curious about where you can find these forecasts produced by the Virginia Institute of Marine Science, this portal is maintained by the Center for Coastal Resources Management where I work. And so you've heard me talk about the TideWatch model. The TideWatch charts provide time series forecasts. And so all the locations that we're incorporating observation data through StormSense, we've been feeding tidal forecasts to those areas, this dashed line representing the next 36 hours looking forward. Just to provide you an example of what this looks like, this is an example of the Newport News number 3 sensor, just kind of showcasing what this looks like. But we use those forecasts to help validate the forecasts that are provided by the TideWatch map, which is a geospatial forecast system. That gives us an idea of the timing and the extent, along with the depth of those locations and the observations collected by NOAA's sensors, along with the USGS sensors and the community-owned sensors through StormSense in coastal Virginia are all kind of conglomerated together. And the purpose behind this is that these real-time observations are leading to very quick response and letting us know whether or not our forecasts are accurate in near real time. And this is another particularly useful resource in the arsenal of flood prediction because it tells us very quickly whether or not the model is approaching convergent flood results and lets us know in real time whether or not those predictions are valid. Now, the way that this model works is this is the TideWatch map. It collects essentially 2.5 gigabytes of atmospheric forecast data. These are weather driven forcings for a model. So they're driven by pressure and wind speeds for storm tide. And of course, tidal predictions, the boundary of our model, and it updates every 12 hours to provide this 36-hour forecast. Now, its spatial resolution is 1 meter or 3-foot spatial resolution at its highest resolution locations, but in more rural parts of the state, this is closer to about 5-meter resolution, and this is relative to the accuracy of the LiDAR-derived digital elevation data we have available at different parts of the Commonwealth. Now, the TideWatch map is updating at noon and midnight, so every 12 hours, as I mentioned, it's taking the latest data available from the National Weather Service, and they're using the NamNest data from the latest updates. They update this information every 3 hours, but we run our model every 6 hours to provide these updates in 12-hour intervals at noon and midnight. Now, in real time, it takes about an hour and a half for this hydrodynamic model to provide a 36-hour forecast, leveraging 72 CPUs from our high-performance computing platform at William & Mary for the Virginia Institute of Marine Science to provide these resources to help people visualize tomorrow's flooding today using the Schism hydrodynamic model. Now, this open source hydrodynamic model is already capable of providing rainfall forecasts, but the digital mapping platform, the bottleneck of the pipeline of providing these updates and incorporating rainfall, when there's a lot more water for the model to keep track of, it takes a variable length of time for it to provide this processing. So we eagerly working on providing a next generation update to TideWatch's map called version 2.0. And so our goal is actively researching this to incorporate the next generation compound flooding model. And so right now this model exists as a storm tide prediction tool, but our goal is ultimately to incorporate rainfall in the near future. So If you're not familiar with how we validate these models, obviously we use sensors as our primary tool, and the purpose behind that is that they're automated. But you can't always just put sensors everywhere because they require maintenance. And of course, the more remote these locations are, the more important the sensors sometimes end up being, and they're much more likely to go offline for a variety of different reasons, as I've covered previously, to cicadas or other strange events that might be happening at the time that record anomalous data. And so additional information to help validate those models is warranted. And so our goal with this is that community science efforts through a program that I help manage along with Wetlands Watch as a nonprofit partner for this effort in the city of Norfolk. They developed a mobile app called Sea Level Rise. And so we've been using that publicly since 2014, but this effort's been coordinated by media groups since 2017, which has involved a large-scale collection of data every year. And we've collected over 250,000 GPS-reported high water marks to help us validate the spatial extent of flooding by our Tide Watch map. Now, the beauty behind this is not only does it help us validate the hydrodynamic models and flood forecasts that we're making, these 36-hour forecasts in near real time, but then on top of that, they're also becoming in their own right, their own observation-driven GPS data forecasts of their own. As we're mapping the highest astronomical tide of the year, we've been doing this for over a decade now, since 2014 when the map exited its beta. But in this case, the Sea Level Rise app and the large amount of data that they've had available have started creating essentially their own interpolated rasters of the maximum flood extent of the king tide each year. And so over the last decade, we've been able to collect that information and help us provide some context to sea level rise predictions, not just in terms of predictions, but this is an observation-driven model. So we're spatially tracking inundation to help produce new types of models to verify the extents that are being produced in sea level rise forecasts. Now, just to give an example, this year in 2024, we collected 22,845 high water marks from 187 individuals that collected data over a weekend that the king tides took place from October 17th to the 20th in 2024. And not only during the highest astronomical tide of the year is this event happening, we have some very avid volunteers that are willing to help us collect data at a variety of different extra tidal flooding events that will take place throughout the year. For example, in March of 2024, we had a high water event on the weekend of March 24th through 26th. And also the highest astronomical tides of September were mapped as a training in preparation for the October highest astronomical tide of the year last year. And so we train volunteers to help us collect these data, but as it pertains to the sensors that I've been covering in this presentation, this provides additional context for communities to say, hey, we have confirmed information that there was in fact flooding here during the highest astronomical tide of last year, and that inundation in the future is likely to happen here. So we coordinate this information with local communities in both rural and urban localities, and we use this to help guide where new water level sensors should be deployed. We have confirmed flooding on the ground in these places to ensure that not only would it be useful in these locations, but that it's likely to become more useful as inundation increases in the context of predicted sea level rise in the future. Now, if you're not familiar with Catch the King, we share data related to NOAA's water level sensors and tidal predictions from VIMS's Tide Watch service at a variety of different locations throughout the tidal region of Virginia, along with North Carolina and parts of Maryland. And in the inaugural year of Catch the King in 2017, we won the Guinness World Record for being the world's largest environmental survey when we collected 59,718 high water marks in a period of less than 6 hours during a single tidal peak in 2017. And so with all the data that we've been able to collect from this year, we'll be doing this mapping effort again. Again, it helps us identify new locations, deploy water level sensors, but also validate hydrologic predictions like the hydrodynamic model Schism driving the Tide Watch map, but also anyone else can actively access the data after these events to help validate their own decision-making for their communities. This year's Catch the King event was taking place on the 10th through the 12th of October in 2025, essentially throughout the entire Atlantic coast of the United States. That's when the highest astronomical tide of the year is predicted to be. Now, if you're not sure what these types of things look like in practice, this is the 2017 example of Catch the King, where we have lots of individual dots populating a map on beaches and in estuarine environments all throughout coastal Virginia. So you can see the histogram there in the top left corner where all the individual points are being collected and the frequency at which that's taking place, but then some little inset maps highlighted there along the mouth of the Lynnhaven River in Virginia Beach, or this example of Norfolk's famous Hague region that mimics the relative uncertainty of tidal fluctuations you'll see relative to the Hague in the Netherlands, for which it's named after. And in this instance, there's a lot of inundation that takes place in these different areas, and so our king tide mappers have helped us map these in past events. We then translate these points as GPS breadcrumbs into a contour map that we can use to geospatially validate the accuracy of our flood forecasts. And so with that, we kind of compare those cell center points, and that gives us an idea of how the inundation is performing relative to what was predicted up to 36 hours in advance. And so that gives us a metric that's essentially just based on a distance formula between the points and the cell center points of what we call a mean horizontal distance deviation between what the model predicted and what was actually observed. And so here's some examples of what our volunteers have used in the past when they look at the Tide Watch map shown there on the right in anticipation of inundation, where there's flooding near Hampton Boulevard, near Old Dominion University and the city of Norfolk, Virginia, compared to points that are collected by the former executive director of Wetlands Watch, Skip Stiles, where he had showcased what the app is capable of doing on mapping out the contours of where the inundation is happening. This also gives us a nice opportunity to kind of describe what those differences look like between mapping on public property and, of course, weird, things that will happen where obviously our models predicted some areas that people can't walk onto private property through backyards to map. But this is still better than nothing in terms of translating that to an elevation. We can then identify that we don't need people to trespass on private property. All these points are being translated to a digital elevation model. If all of these points are confirming that the water elevation was indeed 3.825 feet above mean low or low water, it's probably safe to assume that a lot of places that were that same elevation within a half a mile of that location also flooded at that same elevation. And so, yes, while you might notice that there are some spots that our model may seem to have over-predicted, it turns out that water was in those backyards, so that our volunteers can't go in those places. And so we always advise them to be safe as they're helping collect data to verify the accuracy of these models while still using data-driven assumptions based on that information to help us cover the areas that they can't effectively map or that we can't get drones or satellite imagery of during those time periods. And so our next steps using this information is that I've covered how our StormSense platform works in Tidewater, Virginia. It's ingesting data from the federal government's sensors through the National Oceanic and Atmospheric Administration, along with the U.S. Geological Survey. We have 17 of those sensors total that we've been ingesting in collaboration with them. And their open API links that are shared through their websites. We're also coordinating with the state in Virginia. The Virginia Department of Emergency Management recently replaced what was called their iFlows system with some new water level sensing apparatuses. Most of them are active remote sensors that have been deployed by Greenstream, and so we're working to integrate the public API links with coordination through the Virginia Department of Emergency Management to add those to StormSense for their new deployments that have happened in the last 12 months. And then StormSense has 48 water level sensors currently, but 20 new water level sensors have been funded through Americus to be deployed over the next 5 years. The first of which, as I already covered in this presentation, was deployed in the Pamunkey River last month, and 3 more are still planned by the end of the year in the Middle Peninsula region of Virginia in coordination with localities there. And then, of course, next year we plan to deploy more water level sensors in Hampton Roads. 3 of those water level sensors are currently planned and slated to be machine learning AI water level camera sensors. And 3 of those will be radar water level sensors that are located safely outside of the regions where military installations are deployed in Hampton Roads. And so, in review, we covered a lot of things. There's been a lot of words said and a lot of words on the slides. Sometimes pictorially, it's helpful to represent. We covered storm sense. We have these key performance indicators to let us know in the communities whether or not this information is actionable. A lot of the communities, like the city of Norfolk, for example, have used this to kind of guide rain barrel deployment to collect runoff from roof lines and translate that into geographic information systems for collaborative sharing and a unified kind of visualization platform to let people know, well, what do these floods look like in my community? And so with the data that is provided by the Tidewatch map and the verifications through community science efforts like Catch the King, it helps us identify where inundation is happening frequently and how those might impact transportation infrastructure in the future. And so with that, we're getting a better idea of where inundation is happening in different places. And we're sharing the data from Catch the King along with our model publicly so that planning district commissions like the Hampton Roads Planning District Commission has recently received funding for new roadway flooding sensors. And we're excited to see how we might be able to assist them in that effort, as they're already aware by the communities where there's inundation happening in their localities, but the data that are collected by those sensors are also helpful in validating our forecast efforts. And so targeted notifications and other things are things that are currently being considered along with Waze integration to let people know where there's flooded roadways. Because oftentimes when you have flooded roadways, automated route guidance platforms like Google Maps and Waze tend to lead you down streets that don't have any traffic congestion. But oftentimes the caveat of that is that those sensing platforms are not aware that the reason why there's no cars on the road is because it's flooded. And so this is a rude awakening for people that have recently moved to the Hampton Roads region or Norfolk specifically, where there's a lot of military installations. People not familiar with the location frequently have their cars flooded because they're driving through streets that are deceptively deeper than they look in terms of inundation. And we've won some awards recently for this. We won the Governor's Technology Award in Virginia, or the Commonwealth Technology Award for Flood Vision AI in 2023 for our next generation water observing efforts in collaboration with the U.S. Geological Survey, along with International Data Corp's Smart Cities North America Award won by the City of Virginia Beach for our initial deployments there, and a Smart 20 Award for the in the water category related to the Smart Cities Connect effort. Thank you very much for your time and following along with this presentation, and for Maricruz for helping us deploy 20 new water level sensors in coastal Virginia through 2029, along with many of our community and federal partners that have helped make this observation effort possible.
Thank you so much, Derek. That was a wonderful presentation, and we really appreciate the time that you took to give it. Next, we're going to have Sherry Schwartz, the project manager and operations coordinator for Tetra Tech, who works very closely with Maricruz, give a demo of our OceansMap Insights.
Great. Thank you.
Thank you, Jana. Hi, everyone. I'm Sherry Schwartz, and I work at the Tetra Tech Ocean Science. We are Maricruz's data managers and recently worked with the Maricruz team to develop the OceansMap Insights, which we're continuously improving and which I'm going to share with you today. So let me go ahead and share my screen. Okay. Should be able to see a nice landing page on the Maricruz website. So the OceansMap Insights are pre-made permalinks to interactive map views and dashboards, and they were designed to provide quick and easy access to real-time data for a variety of scenarios and users. There are currently 22 different insights organized into 5 categories, as you can see here, and they're all shown at the top of the page. But I'm going to go ahead and pick one for us to explore. I thought an obvious good place to start was the environmental conditions category. So this is the Chesapeake Bay salinity at max flood versus max ebb insight. And now when you open it up, for those of you who have never seen OceansMap before, especially if you're clicking on an insight or a permalink like that, when it first opens, you're going to see the map and some data visualizations, maybe some analyses preloaded. Just to help you get oriented, like most map-based portals, you can click and drag. You can use this typical zoom mechanism, like a scroll wheel on your mouse to zoom in or out. If I close this drawer, I can also find these zoom buttons down here as well. I'm just gonna click on my station to open that back up. In the top right-hand corner of the Oceans map, we have a few tools here for sharing, collaborating, kind of pulling out some information. So the share this view is how you would generate a new permalink, like what I had when I opened up this insight. We also have a screenshot tool. You can make your own animations of your data changing over time. The Activate Hover tooltip allows you to hover over your data and pull up some real-time information. You can measure distances, use a zoom to box option if you prefer that for zooming. And of course, over here is our legend, which helps us to understand how to interpret the data. On the left-hand side, we have all these icons over here, and these are tools that really help you explore and analyze your data. So this includes our catalog, which if I just turn off this filter, you can see the whole list here of available data sets. And then we also have our virtual stations tool. We have a weather window planning tool, validation statistics. You can create your own custom layers on OceansMap, draw your own shapes or lines. You can change up that base map. I'm going to talk about compare mode in just a minute because that's what we're looking at right here with this insight. We also have our list of insights in the tool within OceansMap and a feedback form. So especially after this call, if you have any questions, feedback, if you ever need help finding access to data, anything like that, please don't hesitate to fill out this form. An email will be sent to me and to the Maricus team as well, and someone will get back to you as soon as we can. All right, so let's dive into this specific insight just a little. So like I said, we're looking at using the compare mode tool in this one. And so I did need to open up my compare mode sidebar here just to really understand what I'm looking at. And first we see these kind of icons next to each of the data layers. So we have our Maricus CBEF salinity layer. We also have our NOAA CBOFS water level layer. And as we can see here, the square is a solid blue line. So that means that it's selected and both layers are on both sides of the map. We could set one layer to the left if we clicked this icon, one layer to the right if we clicked this one, but for now we're keeping them on both. So what is it we're actually comparing between the two different sides? It's actually different times. So for this insight, we wanted to kind of look at kind of the high water level and the low water level at a specific station and how does that change the salinity at that location. So on the left side of the map, I have this set to show data from 7:18 at 2 p.m. Eastern time. On the right side, which is what we see here right now, we're looking at time from 9 p.m. Eastern. So we can kind of see this time is also reflected by the map time dash line on our time series plot. And if I just click this slider and drag it to the right, now my data is, I'm looking at it, it's on the left side of the map. So we're back at that 2 p.m., which is more that high water level time here. We can see not only did this color change to green, which if I open up my legend, I can figure out how to interpret this, but also my value went down to 23 for salinity units. If I move it back, that color changes and we can see the 28. So that's just a little dive into compare mode with this insight, but I'm going to move ahead to the next one. So this one is the navigation dashboard for the Chesapeake Bay. Now we're actually seeing in here, it is a dashboard format, but we have a mini oceans map kind of embedded in the dashboard here. So here we can see some layers are already loaded on the map. We can open a legend, see what we've got showing here. A lot of good stuff, but we can also turn on that Activate Hover tooltip and hover somewhere on the map, maybe kind of where we're thinking we're going to navigate to, let it load for a moment, and it's going to pull up that live data at that spot. So you can get a glimpse at wave height, water level, temperature, etc. We do also have our CBIBS, NOAA CBIBS buoys out here preloaded and some virtual stations and like a channel that we just drew with that custom layers tool for the navigation kind of guidelines. We do also have a table over here. So this is showing real-time data from this Chesapeake Bay buoys York Spitz station, which I put the latitude and longitude just in case you didn't know it was this one right here. The lat long's right there for reference. And then within that table, we have current direction and speed, wave direction and height, and then wind direction and speed as well. I also thought it would be interesting to put the cell signal strength from that buoy here. Might be interesting if you are navigating out, you might be good to know that. I had to look this up, but apparently if it's above -85 decibels, it means it's a usable signal. So that's great. Scrolling down, we also have some time series that are kind of forecast predictions of various various data sets that would be interesting from either the NWPS, we have NOAA CBOS, and I think a couple global forecasting system predictions in here as well. So these are covering everything from tides, water temperature, waves, and currents and winds as well. One thing that I do want to mention before I move on is if you come in here, and really the strength of the insights is that they're a great starting point. You can come in here, edit them, change things around, resave that permalink and keep it for yourself. And then that way it's really customized to your needs. So if you came in here and you really love this Oceans map, but maybe you want to dive into like the full suite of Oceans map functionality, we could do that by simply clicking this unlock button. This allows us to edit all of our widgets through this pencil icon. We can remove any of them. You can grab them and change their size. Oops. Well, I just messed that one up. There we go. Good enough. But also what I want to show you is that if you click this pencil icon, you can grab the permalink. So these Oceans Map widgets are actually used from a permalink, are actually built from a permalink within Oceans Map itself. So if you grab that permalink, open it in a new tab, then you can see the exact same thing and you can really dive in here, start using all these tools, add more data, take some of the data away that maybe is just distracting for you. Maybe you want to draw your own channel, your own navigational route. You could do that too. Just resave that permalink through this tool, create a URL, and you would put it back in your widget and then save it. Once you're done editing, you could also add widgets if you wanted to through this tool. Once you're done editing, you would just want to make sure you click that lock button so you don't accidentally mess anything up, and then create your new permalink. All right, I'm going to quickly go ahead to the next one. So this one, we're looking at another map view, and this is the East Coast Storm Tracking Insight. So here we're really looking at some preloaded data right away that gives a high-level overview of potential storm-related data all along the East Coast. I'm going to open up my legend so that we can start to get our bearings. So we can see that we have, oh, actually, before I do that, I do also want to open up the data layer catalog to show you that the different data sets that we have activated, but also some of these are, I know are set to be transparent, such as the SDOF surge tide. So this one is fully transparent, and what we're actually looking at in this color overlay is the wave height. So that's the one that we see that's fully transparent there. You can change the settings in any of these layers, change color palettes and things like that. And if you click the info icon, it also pulls up some background information on that data. Sometimes or usually there's a data access link as well. Okay. We're also looking at winds on here, which are these barbs that we see. We have gliders loaded, which is great because they're very useful in monitoring, kind of following storm data. And we also have an NHC tropical cyclones active storms layer. When there's an active storm from the Hurricane Center, it will appear with the cone on Oceans Map with this layer, but right now there's nothing out there, so we don't see anything. Okay. Now we do also have a virtual station preloaded at Elizabeth City, North Carolina. So I'm going to go ahead and just zoom into that a little bit. Clicking on it, I can quickly pull up some data at that location. And that's going to give me like the predicted winds, the wave height, that surge tide that I mentioned. But maybe let's say we're interested in a location that's different from this virtual station. This is just kind of an example that's preloaded in the Insight, but you could absolutely adjust this as much as you need. So if you did want to maybe move it a little up here, you could just click somewhere on the map. The data will load, and if you were to click anywhere in here, it'll load a time series as well in this drawer. But I just want to show you how to add your virtual stations and kind of save those to come back to them later. So you can just easily do that with this Add to Virtual Stations button, and you see we got a new label and a new buoy icon as well. And it appears over here in our Virtual Stations tool. So now that you put it in there, you could add more, you could import more virtual stations, you could do a quick add, which just allows you to just click points quickly on the map. You could also edit the station. So if you click that pencil icon, you could change the location simply by clicking set location with a map click and maybe moving a little over there and then click save. You could also just change the actual lat and long. So if you have a specific lat and long that you want to put in, you could do that as well. All right. Okay. And now to the last one, insight that I want to share with you all today. This one is our Virginia Beachgoers Dashboard. So it's a little bit different. It's a little more fun, a little more geared towards recreational users. And it's designed for people who just want to spend some time on the beach. So as soon as it loads, we see some data points right here, giving us helpful information on winds. You know, is it gusty? Are the waves really high? What is the tide looking like? What's the water temperature? And how does that compare to air temperature as well? Because I think I don't want to go to the beach when it's super cold outside either. So we also have another OceansMap widget in here, which is pulling up some data so we can kind of get an idea of the wave direction, some temperature as well. And then just scrolling down, I think one of the real strengths of this dashboard are these weather window tools that are very useful for just planning your day at the trip or day at the beach. So we have two. The first one is comparing both winds and wave height. And it's going to show green basically when when winds are above 7 knots and waves, I'm sorry, it's green when winds are below 7 knots and waves are below 3 feet. Red when waves are above 7 feet and winds are above 30 knots, and yellow if it's in between. So we can see at the times where conditions are ideal, and green at the times when conditions are ideal, and yellow when there may be a little iffy. We may not want to plan to go to the trip or go to the beach at that time. But we don't see any red, which is good. The second one here is showing us water temperature. This one may seem a little bit counterintuitive for our traffic light kind of weather window planning. They're green, red, and yellow. Usually red in temperature plots would mean warm, but in this case, it means it's too cold because the weather window planning tool is really a decision-making tool, like a go, no go kind of tool. So really green is going to show up when water temperature is above 60 degrees Fahrenheit. Green means go. It's a lovely day at the beach. Go ahead and go out there. Red means maybe it's a little too cold. You might not want to go today. And then beneath those graphs, we also have a time series plot kind of showing that water temperature as it's modeled and how that compares to the observations. We have a profile plot of the water temperature as well, in case you like to dive. And some wave height predictions and wind predictions in rose plots as well. All right, I know that was a bit of a whirlwind, but I think that's about all the time we have today. Like I said, please don't hesitate to use that feedback form if you have any suggestions or questions after today. We'd love to hear from this group. And if you are curious about learning more about how to use any of these tools or really dive into them, especially because I didn't have enough time to cover everything, there are some helpful tools that Maricus has on their, or tutorials that Maricus has on their YouTube. So definitely check those out. You can visit their YouTube channel directly, or if you just open up a tool either on the OceansMap dashboard or map view, anytime you open a tool, you'll see at the top this info button, and the tutorial videos are also embedded in here. So you could read the little description and watch those videos and kind of get an overview. But like I mentioned, if you do ever have any questions, don't hesitate to reach out. Thank you, everyone. Back to you, Jana.
Thanks, Sherry. Actually, this is Emily. I'm going to swoop in real quick and just say thank you to everybody for their great presentations, and just give everybody on the call a couple of action items. I've included on this slide, there are lots of ways to connect with us online to get more information as we release more of these insights, to engage with us if you have questions or insights that you'd love to see or want more Maricus updates. So you can find us on social media, Facebook, LinkedIn, Instagram. We're also on Twitter. Please email us at info@maricus.org. Visit our website, maricus.org. Sherry also brought up our YouTube channel. And so I'm going to go ahead and put a bunch of links in the chat so you guys can all grab those as you'd like. I also encourage you to subscribe to our newsletter so that you can get the latest updates from across the organization, webinar recordings, future webinars, all sorts of great stuff. So I'm going to drop all of those links in the chat for everybody to grab. And with that, I'm going to open the floor for questions.
Well, Derek, I actually have a question for you.
Sure.
You had mentioned deploying 20 new water level sensors in the next 5 years, 4 this year and 6 next year, with some of those being the AI webcam sensors. Where are the other sensors planned to be deployed, and what decision guides the type of sensors chosen for installation?
Oh, thank you for that question. So I know right now, just with the certainty of knowing exactly where we're planning to deploy sensors in the next couple years, there are plans for the later 3 years of the project to deploy these water level sensors in Virginia's eastern shore. And so there's Accomack and Northampton County that we've been looking at different locations. We have to be pretty careful about where we select in those spots because most of the cell towers that we have been leveraging for broadband data communication are not the easiest to work with or as reliable for our water level sensors to use those. So they need to be satellite communications. And so we're selecting spots that are most optimal for that, along with places that we can get to them if we need to service them for maintenance. Because there's a pretty substantial amount of inundation. The nearest water level sensor that we've been looking at, the VIMS campus at Wachapreague has a NOAA sensor that's there. But we're looking at locations near Fisherman's Island and others that are not too close to NOAA's Chesapeake Bay Bridge tunnel sensor as well along the eastern shore to deploy a few of these sensors, but also some inside Chesapeake Bay on the other side near Cape Charles. And that would be in year 3. Years 4 and 5, we've been looking at locations along the Potomac and James River as well, a little bit further up where there's inundation that's been observed in the last couple of years. And so while we've covered where 10 of those sensors are located, the remaining 10 sensors will be deployed in those remaining 3 years. And there's new information that we're planning to use as well as we're collecting new king tide flood mapping data in those spots. The second part of your question, I think, was asking about why we choose which types of sensors to deploy where and what types of decisions kind of are involved in that. As I mentioned earlier, some of the challenges we have with deploying water level sensors in places where there's a large conglomeration of military installations is that there's a lot of interference from different types of signals. If it's a location where there's a lot of jets taking off and landing, you wind up with a lot of sonar interference just because the sound and sonic boom of takeoff and landing of jets can be pretty loud. Even if it's not directly focused in the frequency that we're collecting data, we've noticed a lot of strange anomalies that will happen. And so we usually try to use radar sensors in those areas where theoretically there could be radar interference as well, but we found it to be relatively minor unless they're actively trying to interfere with radar signals. And so as a result, we found that in other cases, it's a place where fog is pervasive. The speed of sound is affected by water droplet suspension in the air. So not only is it a weakness for our web camera sensors when it's foggy, but also our ultrasonic sonar sensors are adversely affected by fog. And so we usually will use radar sensors in those locations as well, where fog doesn't affect the conditions of data collection. So all these different types of determinations that are environmental things that might impede accurate measurement are what we take into account in deciding what types of sensors to site where.
Wonderful. Well, thank you very much. And then Sherry, just a quick question. Does anyone else have any questions before I ask Sherry a question? Okay. Sherry, if anyone was interested in having a new insight built or found that there'd be helpful information, is the best way for them to communicate that through that feedback button on OceansMap?
Yeah, I think that's a great way. Like I said, it'll go to both myself and the Maricous team, so then we can come together and discuss that feedback and absolutely explore creating a new permalink and setting up a new insight for that need. Thank you.
Awesome. Thank you very much. Does anyone else have any questions? All right. Well, I just want to say thank you so much to everyone for joining us today. Thank you for all of our speakers, for Tina, Derek, and Jerry, and Mary. We really appreciate your time and working through these projects and sharing all of this wonderful work that you guys are doing with Maricous to a broader audience. So thank you again for all your time, and I hope everyone has a wonderful rest of your day.